आपको बोले तो बोले वो बोले अभी आ रहा है। नेट का इशू तो नहीं है?
नेट का इशू नहीं है।
अब लाइव का
नहीं, ये वाला नहीं, इसमें मैं डाल दिया।
इसमें की डाला तो यहाँ से लेना चाहिए।
इसमें डाल दिया।
हाँ।
ये वाला मैं हटा दिया।
अच्छा, दो OBS है क्या इसमें?
मैं अभी चेक कर दिया बस।
हाँ।
इसमें आ रहा है ना, क्या आ रहा है इसमें? अभी क्या है, एक मिनट में आपको
लाइव तो हो रहा है, दिखा रहा है?
हाँ लाइव हो रहा है। मैं अभी एक काम करेगा इसका लाइव का ये वाला है ना, आपको लिंक आईडी आपको मैं भेजूंगा एक मिनट से।
नहीं, इसको मेल पे भेज के फिर
नहीं नहीं नहीं, डाउट तो ठीक है, पहले एक बार चेक कर।
चेक कर ले। हाँ चल ठीक।
इसमें एडिट करना, इसका लिंक आईडी भी कहाँ से मिलेगा इसका?
अच्छा, मोबाइल से चेक कर लेगा?
मोबाइल से चेक कर लूंगा अभी।
ठीक है, ये भी
मैं आपको भी भेजूंगा, आप एक बार चेक कर लीजिए क्या आता है कैसा आता है।
हाँ हाँ, सही है। उससे फिर उसके बाद अपन
उसके
लाइव
बाद
करते हैं।
उसके बाद पूरा एक बार चेक कर लिया।
वो आज वो ध्यान नहीं रहा, अपन ने नीतू का माइक और वो चेक नहीं किया है।
टाइम भी नहीं होगा, है ना?
आज दिमाग से ही वो स्लिप हो गया।
आप एक बार चेक कर लीजिए सर, इसमें क्या आता है।
चैनल क्रिएट करने का आ रहा है मेरे से। हाँ। वो मेरे को लग रहा है वो लिंक देना पड़ेगी आपको।
लिंक इसके पेज से तो मिलेगा, बट मैं कह रहा इसमें पूरा ये वाला होगा।
हाँ, ये यस यस।
ये वाला है।
हाँ, अब तू उसको भेज मेरे को।
इसमें एक बार चेक कर दो, ये वाला नहीं है, दूसरा वाला। ये नहीं है।
दिस पेज इज नॉट वर्किंग।
बट ये तो सही है सर, इसमें आता है मुझे श्योर है।
मैं अब फिर से एक बार, दिस पेज इज नॉट वर्किंग आ रहा है। थर्ड लिंक पे भेजी क्या तूने कोई?
दोनों भेज दिया, बट एक और बार
फर्स्ट वाली तो तेरा पेज वर्क नहीं कर रहा है, सेकंड वाली
एक मिनट सर, मैं एक और बार ट्राई करूंगा, बट वो आ रहा है, मिलेगा अभी, मेरे को पता है।
लाइव तो हो रहा है?
अभी भी लाइव है, बट इसका ये वाला कैसे उसको दे रहा है? स्ट्रीम सेटिंग, बैकअप सर्वर, स्ट्रीम सेटिंग, करंट व्यूज, हमने दो बार।
स्ट्रीम URL यही तो था, ये है क्या?
इसमें क्या आ रहा
दिस पेज इज नॉट वर्किंग
है ना? इसमें आ रहा है, इसमें आ रहा है, इसमें आ रहा है। Waiting for mix. Just into the इसमें लाइट जा रहा है बट
मोबाइल पे नहीं आ रहा
नहीं आ रहा
है ना, मेरे स्क्रीन पे। यस सर।
The entire display is moving. Just wait for a second. And over here, you just paste it. Like show like 4BVG. Okay, and let's come to here. See 4BVG. It's the same stream. The stream key is different for every live stream. So each time you go live, you have to change this stream. So now the main part that you should not forget at any condition is just click on start streaming. And then when you go right here and click on done, you will find after a little bit of time over here, the entire display is moving. Just wait for a second. Yeah. As you can see, it already came up. You can see over here, excellent connection, and see the live stream already came up. So this is how you're going to see, or anybody going to see streaming you're doing. And then what you need to do is just click go live. So I believe I'm live right now. Let's just check it through my phone. Where it is. Yes, I am. So here is a live stream currently. You can see it where it is. And you can normally live check the way you do in normal YouTube lives. And at the same time, as I told you that, okay, it is. So here is a live stream. So now you can go and you just need to.
got it. Got it. do is should I do is ठाकुर सर, मैं कह रहा कि अभी एक अंशुल अवस्थी नाम से एक पर्सन लॉगिन करने के लिए ट्राई करेगा, उसको एडमिट कर दीजिए सर। अंशुल अवस्थी, एक मिनट, ठीक है।
Working electrode potential with respect to SHE is minus 0.75.
Sir,
Okay.
sir, sorry
Yes.
to interrupt you, but I think you have stopped the sharing PPT. I cannot see it.
Okay. Oh, my screen is visible to everyone, or is it not?
Sir, I can see
But
you
the
right now.
presentation is not visible.
Yes, sir.
Okay. Okay, is it visible now?
Yes, sir.
Okay. Okay, now you see in the present slide, this is a question to all. We have the working electrode potential with respect to SHE is minus 0.75. Okay, we have to find out with respect to other reference electrode, for example, SCE and AgGCl. Okay, so there's a table where different reference electrodes are there, and you need to mention. Okay, so there is one thing more I would like to mention, that there is two things: standard hydrogen electrode and normal hydrogen electrode. Okay, so by the time you consider the same, so what is the standard hydrogen electrode? Is the same as normal hydrogen electrode. Okay. However, there's a slight difference that we'll also understand in the upcoming slide. Okay. So there's a 30 seconds for this question. It's just addition or subtraction problem.
Sir, what is SCE? Standard?
Calomel electrode.
Okay.
This is the Hg2Cl2. So the values are in front of you all. So you can see and tally it, and whether it matches with your value. And now we will further move to, so we are now coming, so everybody has a doubt why the potential is E naught is 0, and if it is 0, then how this the standard hydrogen electrode is working. So this slide contains all this information. Okay, so here we will start how, okay,
Sir, I can't see the slide.
We can see that if we increase the concentration of O,
हाँ सर चेक कर दो
am I
सर
audible?
मैंने भेजा यूट्यूब का आईडी
Sir,
Seems like
हाँ जल्दी चेक कर दो
sir,
ಇದು
we
मैडम
can't see the slide.
So it is visible
एक
to
बार
me.
चेक कर दो
Maybe
व्हाट्सएप पे
this madam are she need to do some settings.
yeah, I think it is visible to everybody except a few. So it may be the problem from your side.
Sir, slide is not visible.
Press the pen bar. Pen bar leads to slide.
Okay, let me reshare it.
हेलो लाइव हो गया ना ठीक है मैं अभी सबको शेयर कर हाँ ठीक है एक मिनट में आ रहा हूँ मैं वहां से शेयर कर दूंगा हाँ ठीक है
Is it now visible?
Yes, sir, it is visible now.
Okay. Okay. So now we'll see that what happens when we increase or decrease the concentration of the chemical species. As a chemical uh, point of view, if you see, the delta G is the Gibbs free energy is associated with the reaction. Okay, first this reaction was in equilibrium, which is having the standard reaction potential E naught. Okay, so we need to keep in mind when the E naught is the potential, then this rate of forward and rate of backward reactions are equal. So it is in equilibrium. Now what we will do, we will play with the concentration of O and R. Now when we will increase or decrease or manipulate the concentration of O and R, what will happen? There's a new equilibrium maintains and that contains a new reduction potential. So we want to find out how the this electrical potential is related to the standard reduction potential. Let's say the new potential is E. Okay. Now we see that the Gibbs free energy change for the reaction is given by this is simple thermodynamic explanation for it, where delta G naught is at a equilibrium condition, RT ln activity of reactant upon activity of oxidant. Okay, reduce species and oxidize species. Okay, in electrochemistry, delta G is defined as minus NFE. Okay, similarly, at equilibrium, delta G will become delta G naught, E will become E naught. We have delta G naught is equal to minus NFE. We will replace all these equations to Gibbs free energy. What we find out that delta E is equal to delta E naught plus RT by NF ln AO upon AR. So this equation is a big equation in electrochemistry. It tells what is the potential of a reaction with respect to the concentration of oxidant and reduced species. Okay. Now this is the activity. Generally, we do not know the activity. And for dilute solution, we know that equation which governs the activity is the activity coefficient into the concentration. Okay. So that concentration and activity coefficients are being replaced by the activity. And now we see that activity coefficient is a constant. Okay. We take this term out and now this whole is a new constant. Okay. So now the new constant is delta E naught dash. Okay. Now if you see that the difference in the last equation and the new equation is the difference of delta E naught and delta E naught dash. Delta E naught was the standard potential of the reaction, standard reduction potential. However, delta E naught dash is the formal electrode potential of the reaction. There is nothing but the activity coefficients are associated here. So it's a new constant. And now the reaction comes in form of the concentration, which is experimentally we can find out. Okay. Using this equation, we have delta is equal to delta E naught RT upon NF ln activity of O upon activity of R. Now we'll come to the problem of standard hydrogen electrode. We say that this is the system. Okay, what we do in the system, that we purge hydrogen gas at 1 atmospheric pressure. Partial pressure is 1 atmosphere. We maintain the concentration as 1 molar. Okay, and in this equation, if we keep the value, and before keeping the value, what scientists assume that for this system E is 0, delta E is 0. So they said that for this system we consider that E is 0, and then they put 0 is equal to delta E naught plus RT upon MF ln of the oxidates and reduced species, and from where they calculated the value of delta E naught. Okay, here what you see, RT by NF ln activity of 2H plus, I mean H plus square. Here the activity, because of a dilute solution, it will become the concentration, and since it is 1, so it will be 1. Pressure we are maintaining at 1, so it is ln of 1. When ln 1 happens, this becomes a 0. So that's why delta E naught will become 0. So that is universally accepted that for SHE, standard hydrogen electrode, the E naught value is 0. Now is it clear?
Yes, sir.
Okay, so now if it is clear, then we will move to our next point, that we will do a simple calculation for a different reaction. We have this reaction. Okay, you have to find out the delta E for this reaction, provided that you have delta E naught 0.54 volt and the concentration of aqueous iodide ion is 0.5 molar. And one thing I also provided, that the value of RT by F is 0.025. Okay, it's a just addition, subtraction, and multiple divisions kind of problem, so it won't take more than 30 seconds. So please do, and then we'll just see. So here's nothing, it's simple. The equation will come like delta is equal to delta E naught 0.54 plus RT by NF. Here N is the value of electron transfer, that is 2, ln of iodide solid upon the concentration of iodide in ecosystem. Okay, for a solid system, activity is 1, and here again the system is dilute, so here the concentration will play a role as an activity. So just replace it and tell what is the value you got.
So is it 1.25, 1.26?
1.26. It seems very high value. Please see if somebody matches with this value.
No, sir, I have to square
Yes,
the
sir.
0.5 value, right?
Yes.
All right, and then after squaring it,
Because 0.5, sir. 0.5.
Yeah, 0.5. I think it should match. It's a simple calculation. It's nothing more. Okay. Okay. So we'll move next. Okay, the slide is not moving. Are the slides visible to all?
yes, sir.
Okay. So now we are coming to our very first slide, where we discussed that we want to calculate the reaction kinetics as a function of concentration and potential. Okay, that's what we said. Okay, the reaction kinetics of an electrochemical reaction depends upon the concentration of oxidant and reduced species and the potential what we applied. Okay, so how do we find out this thing? Okay, so now if you see that this is an equilibrium reaction. Okay, let's say because of some perturbation, let's say some potential, it moves in a net positive direction or a forward direction or a net negative direction or a reverse direction. Okay, so there's an equilibrium happens. So there's the forward rate and reverse rate. There are two a different direction where reaction is possible. Okay, previously, when there is no perturbation of potential, what happens that the forward rate is equal to the backward rate. I forward is equal to I backward. Okay, so that is equilibrium. So net current is zero. Okay, now we are providing a potential perturbation. So now this won't remain equal. So they become unequal, and there's a net flow of current in any of the direction that depends upon the potential. Okay, so we first find out what is the forward uh, rate and what is the backward rate. Okay, so how do we find out? Because before understanding that, I'll just tell one thing, that the system looks like this is an electrode and dipped in electrolyte. Okay, so we consider this interface at x is equal to 0, and as we move, this is x coordinate. Okay, so what is the concentration at any point we take? Let's say if we take here, so this concentration is c as a function of the position x and time t. At time t it varies. Okay, so when we are talking all the reaction happening at the interface, we see we take concentration at x is equal to 0 and at any time t. Okay, if it is of oxidant, then O. If it is of reduced species, this and then it is of T. Okay, so now it would be easier for you to understand these all terms. Rate of reaction, as in chemical engineering, it is defined is the forward rate constant into the concentration of oxidized species, and rate of backward reaction is backward rate constant into the concentration of reactant species at the interface at any time t. In electrochemistry, this is defined as the current which is being produced by NFA. What is N, F, and A? N is the number of electron, F is a Faraday constant, A is the area of electrode which is making an interface. Okay, so this is a projected view. If you see this view, it is like an electrode which is dipped in electrolyte. Okay, so this is electrolyte, so whole area, this area is the area of electrode. So generally what we see is that electrode as a plane surface. However, if you see the microscopic view, this is not a plane, this is a rough surface. Okay, so though we say this is whole area, this is not a planar area, this is whole area. And in this area also, there are certain sites where the reaction happen. It doesn't happen at all the site. It happens only at the electrochemically active sites. So what happens that the ion get adsorbed at the electrochemical active site, and then it react here and then produces product, and that product desorb of the surface. So these electrochemical active sites makes electrochemical active surface area. So we always talk about the electrochemical active surface area. Okay, so here A is electrochemical active surface area. So now we have rate of forward reaction, we have rate of backward reaction. So what is the net movement is the difference of these two, and what is the difference is the net movement or net rate is KF minus KB and that is the net current I upon NFA, which is IC minus IA by NFA. Okay, till this point, it should be clear to everyone. Now, when we see this equation, this is a rate kinetic equation. Now we'll see what are the different factors associated. There's a number of electron transfer, Faradic constant, electrochemical active surface area, forward rate constant, concentration, backward rate constant, concentration. But this reaction doesn't have the potential. Okay. But we said that I should be a function of concentration as well as potential, from where the potential will come. Okay. So that is hidden in Kf and Kv. How? That we will find out from the transition state theory of this reaction. What a transition state theory says. In a transition state theory, we see that when a reaction proceeds from reactant to product, it doesn't it directly convert to product. It makes an activated complex where the standard free energy of the activated complex is more than that of reactant as well as product. Once the activated complex is formed, it is not very much stable. The shelf life is very lesser. Then it convert to the product and the gives free energy release. Okay. For an equilibrium reaction on a reaction coordinate, the stand free energy of reactant and products are equal. It should go like this. This is equilibrium reaction. When equilibrium disturbed, either it moves up or it moves down. Okay. So we will see here what happens. This is a equilibrium reaction where the levels are equal. Okay. Forward and backward rates are constant. I think somebody has opened his microphone, so it's a noise is coming. So please switch off the microphone. It would be easier for others to understand too. Now, if we vary the energy of the reactant leg, this is the reactant leg and this is product leg. Okay. We say this is oxidized species and this is reduced species. Okay. How can we do? We vary the potential. Let's say we increase the energy of electron. How can we increase the energy? By giving negative potential. Negative potential increase the energy of electron. So this lag will move up, gives free energy will move up. Okay, so reaction will proceed in the forward direction. Okay, and on the other hand, if we decrease the energy of electron by providing the positive potential, so the reaction will proceed in the backward direction. Okay, so how much is the change? How does it affect the Gibbs free energy of reactant and product? That we can find out with the help of the transition state theory, and from there we'll introduce the potential in the rate kinetic equation. So let's say we have a system. It looks like very complex system, okay, but it is not so complex. I'll just explain one by one each thing. See this leg, this one, and this leg. These are in equilibrium. That's why these levels are equal. Okay. Now some decrease. So this leg move this here. Okay. Now there's a new equilibrium state, and if you see here, that is zoomed here. Okay. From here, what we calculate, what is the new Gibbs free energy of the activated complex with respect to reactant and product. It's a simple geometry. When it cuts here at certain point, we take this value, some proportion of alpha. What is alpha? This is alpha, and with this found out that what is the relation between the initial gives free energy of the reactant of the redox species, and the final gives free of the redox uh, 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 reduced species. Okay, so what from the equation we find out that G A, the final, is G naught A minus 1 minus alpha F E minus E naught dash. E naught dash, everybody remember this is a formal potential. Okay. Similarly, for the reactant side, we can find out that that Gc is equal to uh, previous value plus alpha times this. Okay. Now we have G of both anodic and cathodic reaction. In the Arrhenius equation, if we keep this value, we can find out the K uh, because that is A exponential to the power uh, minus G by RT. Okay, we can find out the value of Kf and Kv. If we keep these values here, we will find the values comes after the all the calculation. What the value comes is Kf is equal to K naught exponential of minus alpha F E minus E naught, where small f, however it was not earlier present, is nothing but f by RT. Okay. Similarly, we find out Kb is K naught exponential such kind of function. This is just a calculation, there's nothing in it. So what is the conclusion? That is much more important. Here K naught is the equilibrium rate constant. So this is equals in both cases. Okay, now we have Kf and Kb as a function of the potential. We replace in our previous equation, and what we find out? We find out this is a big equation. This big equation is a function of concentration as well as the potential. Now this equation is known as Butler-Volmer equation. Okay, so this equation governs the kinetic of the reaction. Now, how a plot looks like? Okay, we'll see here. E minus E naught is the deviation of the potential from a formal potential. Okay, so we say E minus E naught, or in this case it is written that E naught dash is a formal potential, is the deviation or the over potential. Okay, so what we plot on the x-axis we plot the over potential associated, and on the y-axis we plot how the variation of current happens with this over potential. Okay, how does it vary? We see first only this dash line, this dash line. This dash line say the cathodic reaction which is happening. Cathodic reaction, how does it vary? It varies like if you have positive potentials, then the current is zero, and when it reaches to zero, then the current increases, and in the negative potential, after some time it becomes constant plateau. Okay. Similarly, for the anodic reaction, in the negative potentials, over potential, it is zero, then it gradually increases, and then after a certain value, it becomes a plateau. So this is anodic and cathodic current variation with respect to potential. Now, what is the total? Total is the sum of these two curves, which looks like, which is there here. Okay, so now what we find out from this solid line, that it crosses the x-axis at a current value of 0, where the over potential is also 0. What is say that when the reaction is in equilibrium, there is no flow of current, or we had the equation O plus Ne, this is in equilibrium with R. So when this is in equilibrium, the potential, the over potential is 0, or I think screen has gone or what?
Yes, sir, screen has gone.
Oh, now I think it is visible.
Yes, sir, okay.
Okay, so now we'll see that when eta is equal to 0, or E is equal to, when we talk about the E naught dash, the formal potential, this is the equilibrium potential. Okay, so when equilibrium potential is there, net current is 0, but if we see the anodic current and cathodic current, they are still present there. This is the value of anodic current and this is the value of cathodic current. So anodic current and cathodic currents are present. However, they are equal and opposite to each other. That's why the net current is 0, but they are present there. So this is also we see in chemical equilibrium, that when reaction is in equilibrium, forward and backward rates are constant. That's why net reaction is 0. However, there is a production of reactant as well as product with the same rate. So that's what we see here. Okay. What we calculate? We calculate what is this value of current. For the calculation of current, what we'll do? We'll take any of the cathodic current or anodic current, and let's say we take this. Uh, let's say we take the cathodic current. Okay, this leg, and keep eta is equal to 0. So we take this portion only of this reaction and keep eta is equal to 0. We'll find out what is the value of cathodic current at equilibrium potential. And when we calculate, we just keep E naught, E minus E naught is equal to 0 in the equation. We do not see this portion. We are just taking only one leg. And what is the value of current? We find out after keeping this value as 0. And what we find out that this comes like this value. Okay. Now, this value is I naught is this is known as the exchange current density. Exchange current density is what is the forward and backward constant current is going on in the system at equilibrium. That is the exchange current density, and this is very important. For example, if a system, the exchange current density is very high or very low, so how does it make difference in the system? This we'll understand from this slide. Okay. One more thing, that this equation, this whole equation, just we are replacing this with eta and keeping I naught and replacing in this equation, we get this simplified version of the equation. This is generally you will see as a Butler-Volmer equation. So whenever you see this is the very simplified version. And here, if you see that we have a graph here where 3 different kind of total currents are plotted. One is this vertical line. One is this which is having very high slope, and one which is having very lesser slope. It is actually approximately 0 in this range and then increasing. Okay, so by seeing this graph, can we tell which is having the highest current exchange current density I naught value? Of course, we can say, because this is having the high current. Okay, we will talk about the C first. Okay, so this is gradually decreasing and coming to 0, means this is a feature of 2 curves merging together, where at equilibrium potential they are very nearer. Okay, let's say this is it goes like actually this. Okay, this goes like this. So this is the combination of this curve anodic and combination of this curve cathodic. Okay, when you see at this point, the exchange current density would be very lesser. However, if you see the sharp steep in the current, with respect to over potential, the exchange current density is very high. How does this work in the system? We saw the reference electrode. In the reference electrode, what we saw that we say that the potential of the system, even if it varies, potential, if it goes up or down, the reaction should remain in equilibrium. Okay. If we have this line, what does it say? Though we are moving at a different potential, okay, the current is constant. Okay, current is constant means if a reaction, any reaction, A plus E gives B. If we are varying the potential, the current is not varying, the current is the constant value. Okay, so that's why this reaction have the same kinetics at different potential, and that's what we want in a reference electrode. So for a reference electrode, if we want to prepare, we need a system which is having very high exchange current density, and the curve looks like a vertical line. This vertical line is also known as ideally non-polarizable, which you cannot polarize. Means when you provide the potential, you cannot change the reaction in either of the direction. Okay, so if we have this system, in this system, if you provide a potential, there is a decrease in the current. Let's say if you are decreasing the potential from here to here, then you see there's a decrease in the current. Okay, if there's a decrease in the current, means there's a current flow, means then what happens? There's a net flow in either of the direction, so it won't remain in equilibrium. So what is the take-home message from here? That whatever we want a system to become an ideal reference electrode, we want highest exchange current density. How do we calculate the exchange current density? It's very simple in experimental point of view. How do we do it? We just reconfigure this equation in form of eta is equal to this, and then when we have this equation, we plot eta with respect to current, and when we do it, for doing it, we do a practical experiment that we provide over potential eta in form of some voltage, let's say 100 millivolt, and then 200 millivolt, and accordingly we get some I1, I2, I3 and so on, and then we plot the over potential versus log I graph. And on this log I graph, here it is ln, so if we convert log I into ln, so it is 2.303 factor will come. And then from this equation, the slope of reaction and the intercept of reaction says something. What the intersection says, that where it intersects, you can find out what is the exchange current density. So you take some system, you do some experiment, this experiment, and find out what is the exchange current density. If it is high, it can be useful for a reference electrode. If it is low, you say that it is not worth for being a reference electrode. And then you find out RT by alpha I. From here you calculate the alpha, the transfer coefficient. So transfer coefficient is nothing that tells about the symmetry of the reaction on a reaction coordinate. So for example, this if you see this leg and this leg, the symmetry of the system with respect to y-axis can change on a reaction coordinate. If it is symmetrical, alpha is equal to 1 by 2, and if it is unsymmetrical, let's say it is like this, then alpha is equal to more than 1 by 2 and alpha less than 1 by 2 for a system like this. Okay, so generally in our system we take alpha is equal to 0.5. However, we can calculate it and then show. So from this equation, if you see, now we have come to the conclusion that current is a function of concentration and potential. and this is what we look in the further findings. So what we do is we take the
Sir, you are not audible. Sir, I can't see you. Someone else is looking.
I think he left.
There has been a meeting, I think so. The time is over. The meeting was only up to 1:30.
Okay, sir.
hello.
Yes, sir.
It seems that it's a technical glitch and I could not recognize it. So I would just like to know where I left so that you can explain if somebody is not clear to you.
So you're discussing the exchange current density, how we can find that with the help of a graph, and after that we are comparing the different situations.
Okay, okay, okay. Yeah, okay.
So meanwhile, can you please tell me
Yes,
one thing?
just wait for a moment. Uh, yes, somebody is asking something.
Yes, sir. Sir, in this equation, we are saying that the concentration is dependent on time and the position as well, x comma t, right? And in the place of x, we are writing 0. We are considering it as a 0. But we have also studied that there are a lot of such.
I'm not able to.
Are not audible, sir?
Your voice is not very clear. Yes, now it
Hello, sir.
is clear. Yeah, please tell.
Okay, sir.
Hello.
Sir, in the hello.
Yes, I'm getting your voice. Please proceed.
Okay. Okay, sir. Sir, in finding the potential of backward and forward directions, we have a equation, and in that equation, we are saying that the concentration is dependent on position and time, right? X comma t.
Yeah.
and we are taking x to be 0 all the time.
Yes. Yes.
And also we have studied that there are a lot of electrochemically active sites where this whole phenomena of electrochemistry takes place. So for an instance,
Absolutely.
if at x is equals to 0, the we cannot find any such electrochemically active site. At x is equal to 0, there is no such electrochemically active site. So then, what will happen and why we are taking it 0? This is the main question which I want to ask.
Okay, I understood your question. So let me explain when we say that what is x is equal to 0. This is an electrode. Okay. Uh,
But I can see the screen, sir.
you are not able to see the screen.
No, sir, no, it's visible, sir, visible.
Okay, let me reshare it. Okay, is it visible now?
Yes, sir.
Okay, so we have an electrode. Okay, and that is dipped in some electrolyte. So how does it look like from this side? We see that this is an electrode. There is certain thickness, and this is dipped in electrolyte. Okay. What we are talking about, this x is equal to 0 is the interface. Interface is where the electrolyte or the liquid meets at the solid surface. So when it meets, what it happens that this is the planar electrode. This is a planar electrode where there is a side, and on those side, this electrolyte interacts only. Okay, on this side, the this reactant goes and convert to product. So when it convert to the product, it is still attached to this phase boundary. So this phase boundary, which is in this projection graph, you'll see that itself is x is equal to 0. So it should not be a confusion that at x is equal to 0, there is no concentration of oxidant or the reduced species.
Okay, sir.
Okay, so if we have more question, you can ask quickly, or we will move to our next speakers so that it would be easier for you to understand the experimental approaches in electrochemistry.
Sir, thank you very
Yeah,
much, sir. Gyan Sharma, sir. Am I
yeah.
audible?
Thank you very much. Yes, you are audible. His mic is muted, so we are not able to get your voice.
Sorry, sir. It's a humble request, sir. Please conclude this session so that we can call our next speaker.
Yeah, okay. So I think many of you missed the last
Am I
slide. So
audible?
I'll just go to the last slide of the conclusion so that everybody can understand what we covered in this presentation. So what we covered is we look what is electrode and specifically what is cathode and what is anode and what reaction happens on those cathode and anode. We we worked on the electrochemical cell setup, how do we represent, and which reaction favors in which direction, in what conditions. how do we find out the standard potential of a cell. Then we move to the reference electrode, and we try to find out the value of potential with respect to different reference electrodes. Then we study the potential variation with respect to the concentration of chemical species, and we study the rate kinetics of reaction with respect to the potential as well as the concentration. So that covers the basic of electrochemistry as a chemical engineering viewpoint. How do we do the experimental findings? How do we find out the experimental result, and how do we apply all these things in real world? That we'll see in the first lecture. So, as with this, I would like to end this lecture here itself. And thank you very much for listening for the talk. And if you have some question and query, you can always ask on my email ID as well as on the company's email ID. So with this, I would like to hand over the mic to Dr. Neetu Singh so that he can proceed further for the workshop.
Yes,
Thank you, sir. Thank you so much.
thank you very much, sir, for very interesting and thoughtful session. I hope you learned and enjoyed this session. I request all the participants to ask more and more questions and clear your doubts because it's a full complication. Now I invite Dr. Awasthi ma'am for our second session. He has completed her PhD in experimental electrochemistry from Bharati University, West Bengal. Subsequently, she did postdoctoral research at the IIT Kanpur with the Electrochemical Research and Engineering Group of Professor Ganesh S. Pala. So currently, Dr. Moiti Chatterjee ma'am is the R&D Head of Canopy Technology India Private Limited. So please ma'am.
Yeah.
Continue.
Okay. Thank you for the introduction and good afternoon, everyone. Without further delay, I just want to start. Hello, am I audible? Yeah. Can you hear me? Hello.
Yes, ma'am. Yes, ma'am.
Yeah. Am I audible to everyone? Yeah.
Yes.
Okay. So let me share my presentation. So can you see my presentation?
No, ma'am.
Now?
No.
This button is not working. I don't know.
Hello, ma'am.
Yeah.
Ma'am, am I audible?
Yeah. You are audible.
Please, ma'am, continue.
Yeah. So can you share? Now can you see my screen?
No, ma'am.
What is happening? Just a minute. Let me.
I invite you, please speak.
My screen sharing is option is so I does it need any permission or something from your side?
No need, ma'am. Dinner कर दीजिए.
So this button is not working.
नहीं, उसको स्क्रीन में कुछ प्रॉब्लम चलता है. हमारा प्रॉब्लम कॉल कर देंगे. आप कॉल करेंगे. नंबर है ना जो टिप्स है ना. हाँ हाँ.
I will try by disconnecting and reconnecting to this session. Then it may work.
प्रेजेंट रूम में आप क्लिक कर दिया. हाँ हाँ. उसमें एक और बार क्लिक कर दिए. उसमें एक और बार क्लिक कर दीजिए. जो शेयर स्क्रीन आता है ना, उसमें एक और बार क्लिक कर दीजिए. उसके बाद देन शेयर कर दीजिए. नहीं, इसलिए मैंने बताया जो स्क्रीन है ना, शेयर और एंटर स्क्रीन, उसके नीचे स्क्रीन में एक बार आप माउस में क्लिक कर दीजिए. देन हाँ, शेयर में वो ब्लू इंक में आएगा. अभी हाँ ठीक है. ओके ओके. मैंने कर दिया. हाँ, इट इज कमिंग. ओके गुड. ओके. हाँ मैडम, आप कंटिन्यू.
Ma'am, you are not audible.
Okay, now it's okay. Okay, now you can see my screen and also can hear me, right?
Yes, sir. Yes, ma'am.
Okay, so let's start. So today I will discuss few things about electroanalytical techniques, that is the experimental electrochemistry. So I'm not going to discuss each and every technique, firstly because it is not possible to cover within the given time. And I also feel that if you are learning for the first time this experimental techniques, then it is better to understand a few or only the one basic techniques thoroughly, and then we eventually will understand all the other techniques in a better way. So before I go to the technique, start discussing the techniques, I just want to mention few things about why this attending this workshop is very important, and I just want you to understand the importance of electrochemical science and engineering. So if you look around, you will see many applications of electrochemical science and engineering. So just to name few, this electroplating of metal and hello, can you see me?
Yes, ma'am.
But it is already maximized. I mean, so यहाँ पे क्या हो रहा है मुझे पता नहीं नहीं आपको दिखेगा नहीं तो प्रेजेंट कैसे करेंगे ओके Okay, so okay, so so first there is the electroplating of metal. Then the corrosion is it's a very important applications in corrosion science. So corrosion is basically, we all know, we have some idea about the rusting of the iron or something like that. So basically what we do in electrochemistry, we test the stability of the material when it is exposed to the atmosphere. So we can calculate the rate of degradation by creating a similar kind of corroding environment in the lab, and then we can test the material whether it is good enough to apply for certain purpose. So the thing is, again, this is the very important application that we all know, these electrochemical power sources. So this is the image of a car that is, you may have heard of the company Tesla, that this is a battery operated car. This is the image of the bus that hydrogen fuel cell generated energy. It uses the energy, and the only byproduct is water. So it is not polluting the environment also. So this is very environment friendly application of the fuel cells. This is the solid oxide fuel cell stack that can provide electricity for a whole multi-story buildings. There is a laptop, we use battery in the laptop, and many other things. I couldn't put the picture of all these applications. Also the electrosynthesis, electrochemistry has a very important applications for synthesizing that. Dr. Sharma also mentioned that how we synthesize the aluminum electrochemically. Also, in sensor and biosensor application, also we this is the image of the glucose biosensor. So it detects the amount of the glucose level in the blood. So this is the only one image I have shown. So if you look around, you will see that how important the knowledge of electrochemical science and engineering is. I mean, if you have some expertise, if you be able to gain some expertise in electrochemical science and engineering, then you will be able to contribute to the society and country in a much bigger way. So this is the purpose of the whole workshop, to motivate the students in this field of research. So I will not go through much about the fundamentals, because Dr. Sharma has already covered few of them. But what I just want to touch everything in a very qualitative way. So basically, electrochemistry, what you have learned, electrochemistry is basically the transfer of an electron from it's a heterogeneous electron transfer. So it is between the solid and electrolyte, the electrode and electrolyte interface. So what is electrode basically? Where the electron resides basically. So this is there is something called Fermi level. So you have maybe you know from class 2 level that what the Fermi level is. Fermi level is basically, hello. So can any one of you just keep your speaker on, and just time to time, if let me know that whether I am audible or not, something like that, so that it will be easier for me to.
Everything is fine.
Yeah. So just if I ask whether I'm disconnected or not, that is. So this is the Fermi level, and the Fermi level is the highest occupied energy level that an electron can occupy at absolute zero Kelvin. So for conducting an electrode, electrode should be a conducting material. Electronic conductivity is important for to be an electrode. So in metal, specifically if you use a metal as an electrode, you will see that this conduction band and valence band overlaps. According to band theory of the solids of metal, this two band overlaps, and this conduction is possible when the partially filled valence band electrons can be raised in energy by external field. So this is very important. And also this Fermi level in electrochemistry, this Fermi level we associate it with the electrochemical potential of an electron. Now just simply just imagine if we put a platinum wire inside a electrolyte solution containing this ferrocyanide ion. Okay, so here this is the plus 3 state ion, and there is a plus 2 state ion. So what will happen? So first, when there is no electron transfer, so the Fermi level of this ferrocyanide ion and the Fermi level of the metal electrode is different in energy. But once they come in contact with each other, this energy level will try to equalize, and they will try to attain a new equilibrium. So then what will happen? This energy, this is the dotted line shows here the original position of the solution energy level, and this is the original position of Fermi level in the metal side. So they will try to equal to attain the new equilibrium, and then the electron by transferring the electron between these two levels, they will interchange the electron. So electron transfer will occur within the interface, and they will establish a dynamic equilibrium. So this electron is from metal side, and this equation, as explained in earlier lecture, there is something called Nernst equation. So this charged interface will give origin to some electrode potential. And this electrode potential can be related with the concentration of the species. Originally, the Nernst equation is in terms of activity, but here I have written it is in a concentration form, and it was explained earlier that once we represent it as a concentration, we will call this one as a formal potential. So basically, in electrochemical techniques, we measure this formal potential. We deal with the formal potential, not the standard electrode potential. So these things already has been discussed, so I'm skipping this portion. So now we had one platinum wire inside the solution, but it is very difficult to measure the absolute potential of a single electrode. So we need something to measure the potential of the electrode. But if I put here the hydrogen electrode, then hydrogen, as explained earlier also, this hydrogen we assume as a zero potential. So this is just a scale, because just as like we measure 1 meter, 2 meter, we have 1 meter as a standard. So with respect to which we measure the other distance or diameter, something like that. So it is basically a standard. We assume that hydrogen is this reaction, hydrogen electrode corresponds to this equilibrium reaction, and according to Nernst equation, we can calculate the potential, and we assume the potential as a electric potential as a zero. And with zero, if we measure anything, any potential of any pair, so that will be equivalent to an absolute potential of a single electrode. Am I clear to all this portion? Because there was much confusion about this in the earlier lecture. So
yes, ma'am, it's clear.
And now this potential, these single electrode potentials, all this you will find some table in the table form. So that already was explained. So this is a standard reduction. Basically, they don't mention the reduction potential, but basically all these reactions are reduction reaction, and this is the standard reduction potential in aqueous solution. All these reactions. So this table we sometimes we consider to calculate something, but these are these values are all theoretically calculated. So in experimental condition, when we do actual experiment, if we take some reaction, suppose you are depositing nickel or tin or something, the value is not exactly this one. That I will explain why there is kinetically things are different. So thermodynamically we can predict some value, but the kinetic in reality, when we do the experiment, it differs from what is predicted by theoretical calculation. So this is a typical picture of electrode-electrolyte interface. So there is many model that has been proposed. Still people are working on this to propose some model about this electrolyte electrode interface. This is just a model where you will get some idea about what is happening in the molecular level. So here, if you assume this anions are specifically absorbed on the electrode surface, so here you can see that the metal is negatively charged, and the metal here, and there is an compact layer just adjacent to the metal, and there is another layer that is diffused, and this is the outer Helmholtz plane, and this is the inner Helmholtz plane. Helmholtz is it's named after a scientist, so that's why you call it Helmholtz plane. So this model is given by there is many other models, Stern-Helmholtz model, something. So I am not going in detail discussing. So this double layer looks, it forms a double layer kind of thing, and this is similar to a capacitor. It behaves like a capacitor. So this just keep this picture in mind. that why we call this electrode-electrolyte interface, why we compare it as a capacitor. So this is actually what is happening in the electrode surface region, and this I want you to keep a mental picture of this, because this will help you in understanding the electrochemical techniques and also interpreting the results of the experiments. So what is happening here? The mass transfer, the reactant is coming towards the electrode surface. They may or may not undergo some chemical transformation before coming to the electrode surface. Then the absorption will take place, and after the electron transfer, the product will dissolve from the electrode surface. New reactant will come, and also after getting reduced, this can also undergo some chemical reaction, and then it will move from the electrode surface, move away from the electrode surface. So this movement is basically the mass transfer. We call it mass transfer region, and this is the chemical reactions. When it happens with the electrochemical reaction, we call it as a coupled chemical reaction. So different electrochemical techniques, through the different techniques, we can detect this, whether the reaction is only electrochemical reaction or a chemical reaction is coupled with that reaction or not. So we will come back again if needed, because this picture is very important. We sometimes will explain the result on the basis of this picture, this diagram. So mass transport is again there is 3 types of mass transport. One is convection, so that is mainly caused by the movement of solution. Mechanically, we can start the solution, or the rotating disc, if we use a rotating electrode, so that will create a convection. And there is another type of mass transport, that is migration. So that mainly happens due to the charge particle. Some particle will attract, opposite charge will attract, and same charge will have repulsion. So during that, due to this force of due to this interaction, there will be movement of the particles. So, and the most important is the diffusion, because we have this diffusion is more defined, and we can the electrochemist can measure the diffusion, there is this Fick's law, these equations are available. So we try to eliminate all other mass transport, because this migration we can eliminate by adding the supporting electrolyte, and convection if you use an unstarred solution. But so we try to concentrate only on diffusion, because it is easier to calculate. So, but in a solution, all these 3 things, 3 types of mass transport occurs simultaneously. So it is very difficult to calculate that how much they are contributing to the total mass transport. So the Nernst-Bank equation actually gives us the combination of all these 3 types of mass transport. So now I'm quickly just finished fundamental things, and now I just there is a main thing that I want to discuss. So there is experimental electrochemistry. So there is something that I want to share, that so far from class 2 level, whatever you have learned is mainly we just whatever calculation, that how you are calculating from standard electrode potential, what will be the cathodic reaction, what will be the anodic reaction, what will be the cell voltage, all these things we mainly dealt with the equilibrium electrochemistry. So now what experimentally what we do when we measure some, we use some technique, we disturb that equilibrium, and then we study that how the system is approaching towards a new equilibrium. So we give some perturbation, and that perturbation mainly is the potential. So for 3 electrode, for electrochemical experimentation, we use typically a 3 electrode electrochemical cell, and here the already this has been explained that what is working electrolyte. The working electrolyte, we doesn't define that what is cathode, what is anode. We don't define it in that way. We just say it is a working electrolyte. So sometimes it acts as a cathode, and sometimes it acts as a anode. So when we study oxidation reaction, we said it is anode, and when we study as a cathodic, some cathode also we said it reduction reaction, we said it is acting as a cathode. So it is basically the working electrode, and this is the main it is the main focus. I mean, where we study all these electrochemical processes. Whatever is we want to study, that is it happens on the working electrode. And reference electrode, that you already know that it has a constant electrochemical potential, and it helps to control the potential of the working electrode. So if you want to apply some potential, particular value of potential, we measure it with respect to the reference electrode. And the counter electrode basically completes the circuit. So something happens in the working electrode, because if some reduction is happening here, so the there must be some simultaneous oxidation reaction also, because we cannot just do the reduction. If you do the reduction, there will be an oxidation also. So it's a redox reaction. So if we study the oxidation here, the reduction will take place somewhere. So that is the counter. But it is very important. We cannot characterize what reaction is taking place in the counter electrode, and also we cannot control it. I mean, suppose if we are doing some water electrolysis reaction in the cell, so if we are studying the oxygen evolution reaction on the working electrode, the hydrogen division will take place on the counter electrode. But it is very easy to say for a water electrolysis reaction, but in many cases where the reaction analyte is a very complex thing, we don't know what is the actual reaction is taking place there, what is the counterbalancing reaction. So there may be some couple more than one reduction reaction maybe there take place. So basically what we do, and also we have to make sure the kinetics of the counter reaction doesn't interfere with the working electrode kinetics. So we take a very larger area counter electrode compared to the working electrode, and so that eliminates the kinetic effect of the working electrode, counter electrode reaction, sorry. So here we can, I have expressed the dotted line, that how the connections are made in the electrochemical cell. So working electrode is connected with the reference, and working electrode is also connected with the counter. But reference electrode there is no current flows through the reference electrode. It just for the controlling the potential. It just measure the potential difference between these two electrodes. So in actual practice, this looks more or less like this. So here is the cell setup. I have shown some analyte here. So I've connected with this one as a working, this one as a counter, and I put reference to a separate chamber, and I connected through a salt bridge. So this is how a typical electrochemical cell setup looks like when we do the experiment. We do some experimental characterization of some analyte or some electrode. So this is typically a bit different than what we have seen in equilibrium electrochemistry. We only just took one zinc and copper chamber, and then we connected with salt bridge, and then we measured what is the potential difference. So this is a bit different. Here we only study half cell reaction, that is whether it's oxidation or what is happening in the working electrode. We are either oxidation or reduction. we can only study the half cell reaction here. And if you want to study a full cell reaction, that is you want to fabricate that zinc and copper, then you will measure the potential difference and all the thermodynamical parameter you can calculate, that what is the cell potential of the whole cell potential. So this is typically this is our instrument, the electrochemical workstation. There is two kind of technique we use. That is a potentiostat and galvanostat. So basically, a potentiostat measures and controls the potential difference between the working and the reference electrode, and it also measures the current flow between or working and the counter electrodes. And a galvanostat applies and measures the current between the counter and working while measuring the potential between the reference and working. So if we go through the techniques, we will make it more clear. So potentiostat is the techniques is basically nothing. We apply a voltage, and voltage is always a function of time. So we create a voltage waveform through the potentiostat, and the different techniques uses different kind of voltage waveform. So what does it mean? Suppose this is a linear sweep voltammetry. So what we use, here we just sweep a potential with time, and this is the technique that is called the linear sweep voltammetry. And now if we create a voltage waveform like this one, this is called a cyclic voltammetry, because see here the initial potential and the final potential is same. So basically what we are doing, we are just returning back to the initial potential. So it is completing a cycle. So that is a cyclic voltammetry. And there is another chronoamperometry. So this is we are applying a constant potential, and we are measuring the current, that how the current is changing with the potential. So this is the waveform basically, and how it looks in the instrument, how the experimental data looks, that I am coming. So now I have connected this cell with the instrument. So this is the working electrode lid. This one is the reference, blue one is the reference, and the black one is the counter electrode. So we will connect the instrument, and this instrument will be connected to the software with the PC, and when we run the techniques through the software. So now suppose, for example, take the this one is an electrolyte. Take potassium ferrocyanide and potassium ferricyanide. So you have this these irons in two different oxidation state. So if we basically electrochemistry, we need something that can be detected through the transfer of electrons. So that is basically the oxidation reduction reaction we can study. So those molecules who are not electrochemically that cannot change the oxidation state, we cannot detect those molecules through the electrochemical techniques. Okay. I mean, there is some other techniques also. This impedance also we can check the resistance, but for now, just we need something that changes the oxidation state. So suppose we are taking this platinum wire and also the reference electrode as a silver chloride electrode, and we have taken this counter electrode as a platinum mesh. So I have shown you the image of earlier also. Yeah, this is the platinum coil. Basically, mesh looks like a square net kind of thing. Now, this is what I am going to perform. I will do a cyclic voltammetry experiment. So, what is cyclic voltammetry? I will. This is a potentiostatic technique because I am changing the potential. I am applying some voltage. We are starting the voltage as a 0. Then I am going to a maximum voltage, and then I am coming back to a minimum voltage, and then ending the voltage at 0. So here we have some options choosing the number of cycles also, and this is the current limit is very important because it depends on the analyte, that how much the current will be. The concentration of analyte, the current varies directly with the concentration. Let me show you some animation, it will make you the clear. So this is basically what we do with the potential stat. This is if you remember what I mentioned earlier about the Fermi level of these two species. So basically, when we provide potential energy through the potential stat, we are providing the electrical energy through the potential stat. We're increasing the energy of the electron, and when it goes up, the electron transfer will take place, and when it goes down, electron transfer will take place in that direction. So in one direction, the reduction is taking place, and in other direction, the oxidation is taking place for this particular species. We can I just made this diagram for this ferrocyanide system. So you will see the oxidation state is also changing through the electron transfer. So it's just like a water level. I mean, if you increase the water level, water will flow on the downward this side, or if we decrease the water level, water will flow this side. So it's just a flow of electron, and we play with the energy level through the potential stat. So now now this is the actually what we observe experimentally. This we when the oxidation is taking place, we will get a peak when the transfer of, if you remember just the previous slide, when the electron is electron transfer is taking place. Whenever the electron transfer is taking place, we will get a peak current. So the current will, with the flow of electron, we will get the signal of the current. So here, actually by convention, we take this positive current as a oxidation current, and this negative current as a reduction current. So this will we'll see the ferrocyanide system, and this kind of cyclic voltammetry curve it will show. So this is basically when we start this, we call as a so sign convention I have told you. So sometimes you will see that just the inverse of the curve. Sometimes you will find, and the parameter that we need to set up, because I know this system will show oxidation potential, oxidation peak at this particular potential around 0.3. We are getting this oxidation peak. But maybe you are working with some unknown system that you don't know that at what potential it will get oxidized. So in that case, choosing this potential window is very important. That where you can detect the oxidation and reduction of that species. So voltage, choosing the voltage window is very important. Also, if you are working with an aqueous electrolyte, the aqueous electrolyte will, the solvent will, the hydrogen evolution and the oxygen evolution will take place in the extreme end of this potential window. So we don't want to, this solvent stability puts some restriction of the potential window also. So, and also the supporting electrolyte, whatever you are taking, here in my case, I took that KCl. So it should not, it should be stable within this potential window. So there is three factors. If you choose the, when you choose the analyte, that your experimental conditions, so you should choose the analyte, the supporting electrolyte, the solvent properly, so that you can detect the electroactive species properly. And also the scan rate. because if it's a very this ferroferricyanide is a reversible reaction. Because reversible, we call reversible because we are getting the oxidation peak and the reduction peak. This current is the same. Okay, so how we measured, I will come to the next slide, then it will be yeah. So this type of voltammetry, it is a reversible voltammetry. Reversible, what we call reversible is that this current value, this anodic peak current and the cathodic peak current are equal and opposite in sign, and also this peak difference also have some particular value for this reversible system. And from this CV we have different regions. This is the capacitive current. Here we don't see any electron transfer. No electron transfer occurs in this region because the current is not. We are not getting any current here. So this is basically the capacitive current. This is the non-Faraday zone. Faraday current means that there must be a electron transfer occurring, and that is the Faraday current will increase very sharply here, and this is the Faraday region. So there is two types of current we get. One is capacitive current, one is Faraday current. Capacitive current is mainly that there is no transfer of electron. It's only charging the double layer that I have mentioned earlier. So it is just creating a charged interface region. So this is the capacitive region, and here we are getting some peak. So the potential corresponding to the peak current is a peak potential, and the potential corresponding to the peak current of the cathodic peak is the peak potential of the cathodic current. So there is many things we can calculate through the cyclic voltammetry experiment. We can calculate the over potential. Over potential is basically this two peak, oxidation and reduction. If it should how much it is differing depends on the over potential. So over potential has been explained already, but I will show you another animation that will clear you what exactly I meant for over potential here. So here the diffusion coefficient can be calculated with this Randall-Sevcik equation. Here we plot, we see that with the scan rate, if we increase the scan rate, the current will increase. And with the increase in scan rate, if we draw a square root of the scan with this equation, if we put the square root of the scan rate here and the peak current value here, so you will get a intercept, get a slope. From slope you can calculate the diffusion coefficient of the reaction. So diffusion is the so that's why I said that diffusion coefficient is easier to calculate. That it gives you, this is the basically mass transport thing, that how fast the diffusion is taking place. And there is many kind of cyclic voltammetry, many kind of systems that can be reflected with the, you can differentiate that how the system is through the cyclic voltammetry study. So this is basically what I have shown. This is the reversible system, and this one is the extreme. This C is a irreversible system. So what is happening here? Something is getting oxidized, but we are not getting any reduction peak. So this is basically something that is the reduction, either the reduce if you say it is a Brovin evolution reaction or something like that, then we will not, the other species will leave the system as a gas. So we will not get the reduction peak. And also if something is getting oxidized and the product that it is transforming into, that is not electroactive. So we are not getting any reduction peak here. Okay, so this is a irreversible system basically. And this one is intermediate, this one is a quasi-reversible. Quasi-reversible is something that is in the low scan rate, it is behaving as a reversible reaction, and with increasing the scan rate, these two peak separation will improve. This peak separation will increase. So in general, reversible system up to certain scan rate, it will not, the peak separation will not increase. It will remain fixed. So this is an animation. It will show that earlier I have seen, I haven't put any energy barrier between the electrode and electrolyte. So here, this energy barrier is the actually creating the overpotential. So if we suppose the energies became favorable, I mean, for the electron transfer, but still the electron transfer is not taking place because of this energy barrier. So what we are doing with respect to the potential, by using some non-spontaneous reaction, we can also make the reaction possible by increasing the energy of the electron, and that will help the electron to overcome the potential electrochemical, this overpotential barrier. So it's just like the free energy activation energy barrier, what we have seen in the free energy reaction coordinate versus the free energy diagram. It is the overpotential is equivalent to the activation energy barrier. You can compare these two kind of energy diagram. So here the corresponding, see that's potential, this peak difference, peak potential already, this is the difference has increased because of this overpotential. So whatever has been explained in earlier lecture, that is that by Butler-Volmer equation, we have deduced what is the overpotential thing. So experimentally we can feel like this in this system, that what the role of the overpotential. If we even if the thermodynamically we can predict this equation can happen, the overpotential limits the possibility. So here is different kind of cyclic voltammetry diagram, and this is the linear sweep. The waveform looks like this. So linear sweep basically different from cyclic voltammetry in one sense that cyclic voltammetry I am just sweeping the potential for one whole cycle. So I am also studying the oxidation and also the reduction portion also. But in linear sweep, we only linear sweep is only unidirectional. Either we will see the oxidation, but either we can sweep towards positive to negative or negative to positive direction. So it just enables us to study only one side. So typically it is studied to check the onset potential of the gas evolution. Suppose this one is the hydrogen evolution reaction. So if we compare it with the, if we take a acidic solution, so we will see that if we sweep the potential towards the negative direction, the gas evolution will take place here. And you can see in the electrode that there will be bubble of hydrogen gas. So the setting typically takes you set a start voltage and you put a end voltage. So it can negative and it can go to the positive side also. So there is another technique called chronoamperometry. So this is basically chronoamperometry is basically we do in a constant potential technique. So we if we know something that is we know some oxidation potential of something or some reduction potential of something. Suppose you are depositing a metal on some substrate. I will demonstrate the copper electroplating experiment on the third day. So if we want to deposit some metal on the electrode surface, we are applying a constant potential. We know that what potential will before the deposition we will determine that what is the exact optimized potential for deposition, and then we will use that particular potential, and that electron, the copper will get reduced at that potential, Because see, in the earlier cyclic voltammetry diagram, we from the cyclic voltammetry we saw that where the potential, which potential corresponding to the oxidation potential, the peak potential, we can determine from the cyclic voltammetry that where the oxidation is taking place, where the reduction is taking place, and we can choose from this cyclic voltammetry experiment that what should be the ideal potential where I can deposit the metal. So this is the chronoamperometry technique we use for typically for if you want to electrodeposit something on. So you use a constant potential, and there is another called chronopotentiometry technique. There we use constant current to deposit metal. So this is basically the Faraday. There is I mentioned earlier there is two kind of current. One is Faraday and one is non-Faraday, that is capacitive current. So it basically charge the interface, and this one is where the electron transfer, when the electron transfer is takes place. So that gives rise to Faraday current. So this current, if we apply a potential step, suppose we are applying a potential for a short duration of time or some duration of time, and then if we withdraw the potential, we stop applying the potential, what will happen? This Faraday current will decay in a slower rate than the capacitive current. So basically we use another technique, that is a pulse voltammetric technique. We use pulse and we eliminate the effect of the capacitive contribution, and that will give a better resolution of the peak. So these are a bit difficult to understand. I mean, I think it's not difficult. The process is not difficult. If you do the experiment, you will understand that. Here, basically, chronoamperometry. What we are doing, we are applying a fixed voltage, and we are this is the actual experimental observation. So we applied a constant potential, and then we are getting a current response, and the current response is that it is first it is increasing, and then it came to a constant value. And this is basically, I took, if you can see my screen here, actually it's very small. Can you see my screen properly? Hello?
Yes, we can see your screen.
Okay. So here actually it is only for the blank, the red one. I didn't take copper here, and there in presence of copper. So copper deposition is taking place because we are getting some amount of current. The current has increased, the negative current. So that is a reduction process, because negative current, I have told you that this negative current corresponds to a reduction process. So here we can see this is the typical chronoamperometric response for the electrodeposition process. So Butler-Volmer equation already has been explained. So I'm skipping this portion, but this equation is important to understand, because the next experimental technique that we use for to detect the corrosion, to characterize the metal corrosion, this equation is approximated to some Tafel equations, and this will give you, suppose you are plotting a in the exchange current. I think this has do you want me to explain this? I mean, I'm because that time already the screen there was some connectivity issue with when Gyan was explaining this. So basically here what we do, this is an overpotential versus current plot. So a log I plot, logarithm of current. So overpotential, you already I guess you have some impression about what is overpotential. It is that E0 minus E0, basically how we are perturbing the potential from the equilibrium value, that is the overpotential. So we are giving a perturbation, more the perturbation is, more the current will flow like this one. So here we will get us, if we draw a slope here, The idea is for a corroding metal, we will see that if we change the equilibrium potential, if we part of the potential, deviate the potential from the equilibrium potential, how the rate will change. So that will give us an idea about that how the corrosion, what is the corrosion rate of that particular material. And this corrosion rate, if it is high, then the metal is unstable in that medium. And this corrosion is low, then we can say this is a better material. So this is actually the plot that we get. This is the voltage versus log I plot. This is a TAFL plot. So we in our software we just we choose two different values from the linear portion, and we get the intersection of these two slope, and we get the E core value. This is the E core and I core, and then we calculate the corrosion rate, because now we got the anodic TAFL slope and cathodic TAFL slope, and from that we can calculate that what is the corrosion rate using the formula of the corrosion. And this is the basically the corrosion analysis. We just a material. We suppose you take a iron nail in some salt solution. So how stable it is within this salt? We create an environment for this corrosion. So if that's in that way we characterize the corrosive property of the material. If you synthesize some material, you can characterize the corrosion. And this is the differential. There is many kind of pulse voltammetry, normal pulse, differential pulse. So there is. I will explain just one of the technique. Here I have. This is the differential pulse voltammetry. This is the kind of waveform we use here, because what I explained earlier, that basically the techniques differ from how we are creating the waveform. That is, we are changing the voltage with time, how we are creating the waveform. That defines the technique. So there is the initial potential and a final potential here also. But we apply some voltage pulse for certain duration, then we will draw again, and we come back to a different potential than the initial potential, and this is basically the step jump. So we are increasing the potential to reach the final potential in stepwise manner, and also we are keeping the potential for certain duration, and then we are withdrawing, and we kept our measurement time to the just before the pulse ends. We are measuring the current at that time. So here basically what happens, the curve that I have shown, that the Faradic and non-Faradic, this decay of current, when we withdraw the pulse, the decay of the decay rate is different for the Faradic and non-Faradic current. So when we are using the differential pulse voltammetry, the idea is to eliminate the non-Faradic contribution as much as possible, so that we can get a better resolution of the peak. This kind of voltammetry gives a very it's very better for detection. It has a very low detection limit. So for this, for example, this is the for ferrocyanide couple. I did a reduction, only the reduction side of this pulse voltammetry. So it see here the background is almost corrected. I mean, we are getting zero current. So this background correction has already been done because of non-Faradic, whatever from the supporting electrolyte, we are eliminating here.
क्या है?
And this is a very
नहीं जो तुमने भेजा मुझे
and already so by carefully choosing the parameters, potential, we can increase, we can optimize the resolution of the peak. So in general, this technique is very useful for detecting very low concentration of analyte, and that is for suppose we want some heavy metal detection of some water sample. So it is in the ppm range. So in that case, we can use DTV technique. So now I will just quickly go through this impedance technique. What is electrochemical impedance is basically we apply a very small perturbation from equilibrium or some particular potential. Either it's an open circuit potential or some other potential. Either the potential we can choose from Faraday region or non-Faraday region. So it can be an applied potential or it can be an applied current. So depending on that, impedance is either it's a galvanostatic or potential static mode we can do. So the response is the response to the applied perturbation is generally sinusoidal and can differ in phase and amplitude. Let me show you. So actually impedance, the main difficult part of the impedance spectroscopy is you have to hello, can you hear me? Hello.
Yes, ma'am. Yes, ma'am.
So I think everybody is feeling so. Hungry.
Yeah, we can hear you. Yeah.
Okay. Okay, I will take only I think more 5 minutes. So this is basically the equivalence electrical circuit of an electrochemical cell. So I actually mentioned where I mentioned that double layer capacitance, double layer picture of the electrode electrolyte interface. So that is this is the capacitance kind of thing. Okay. So this electrode electrolyte interface can be pictured as an equivalent electrical circuit, and that is called equivalent electrical circuit. So for a simple system, suppose we have a solution and this is the solution resistance. We have an electric double layer, that is the capacitance, and we have this is the constant phase element we say, and this is a simple electrical circuit that we can associate with a simple electrochemical system. But if other reaction takes place, other reaction couples with the simple electron process, then the circuit will be complex. So main thing is we will get some result and we will fit this result with some circuit. We have some we have to do some combination. We have to combine different circuit elements, and we have to see that which matches the result. And accordingly, we can calculate what is the capacitance value, what is the solution resistance value. We will get that value. So basically, see this the earlier whatever the circuit picture I have shown. This corresponds to this kind of impedance spectra. So this is the simple electron transfer reaction, and this region we call is a kinetically controlled region. This is the mass transport limited region, diffusion control, and this is the solution resistance. From this, the intercept is R omega is the solution resistance. So this kind of basically what we do, we get some either we get one semicircle, or sometimes we get two semicircle, or sometimes we don't get any circle at all. We get only the line. So this defines what kind of system and what kinds of we can come to what kind of equivalent circuit they represent the electrochemical system. So this is the difficult part is to get an equivalent circuit model for the whatever experiment result we get. So this is for some I took some paper. It is from some research paper. So this is they have studied ITO electrode. So this is a typical kind of experimental result that they match with an equivalent circuit like this. So from this, they have calculated all the parameters of what the system, they characterize the interface or how the system will behave. So it is very, actually, if I want to say, there is many things to understand, but for now, these are the reference textbooks that if you want to learn electroanalytical chemistry in a better, you have to read all these things, all these books, especially the electrochemical methods and fundamentals and application. This is the Alan Baden-Stockner book. This is very good book. This is the Bible for electrochemists. So, any questions? So I'm done from my side. So,
can you tell me about something about AC voltammetry? I mean, you didn't include that thing particularly.
What?
Alternating current voltammetry, ma'am.
Alternating current voltammetry. No, I didn't include. See,
Yeah, that's what I'm asking.
Yeah, there is many kind of techniques. I mean, there is I didn't cover. I only covered some basic techniques, but alternate current. I don't have much idea about that.
Oh, no issues, ma'am. No issues.
Okay. So anyone?
Hello, student. You can ask anything about this electrochemistry if you have any query.
Hello.
Hello.
Students, if you have any query, you can ask. Please feel free to ask. I think all are satisfied with your presentation, madam.
No, I think they are hungry. That's the thing. So they are maybe I went very fast also. Few things I wanted to.
It was a very nice presentation.
But definitely third day when I will do the experiment. So we have shared a question this sheet with you, right? This. So for the students, so there I have put some questions there regarding this copper electroplating. So better they will just check the questions first, and then I will describe some 10 to 15 minutes about the experiment that I will perform, and then we'll go do the experiments, and after that they can ask that whatever if they have any doubt, because experimental things, the more you do the experiment, it will become more clear. So
it will be benefited for students. So.
Yeah, they can ask me anytime, and also they can drop email if they have any queries.
Student, you can also write a mail if you have any questions, so you can write in the chat box.
Anything. I mean, they can ask anything, and now also, yeah. Okay, so
Okay, so ma'am, I think all are satisfied. So I'm thankful to you, ma'am, for a very nice presentation on analytical methods in electrochemistry and application. So thank you. And student, tomorrow we will start this online workshop at sharp 11:30. So first lecture will be delivered by Sri Anshul Awasthi, director and co-founder of Canopy Techno Solution Private Limited, and the topic will be a topic on water quality analysis. The second lecture scheduled at 12:30 to 1:30, and the talk delivered by Dr. Gyan Prakash Sharma, and the topic on the topic of solar hydrogen generation, the future of green chemistry. The same link of Google Meet and YouTube live streaming, both link will be same. So we will meet again on this link at tomorrow. So I'm thankful to Madam M. Chatterjee and Dr. Gyan Prakash Sharma for a very nice presentation. Thank you. Thank you all. Thank you, Madam.
Okay, bye. See you.
Thank you. Bye.
Thanks.
Can we leave?